So today, let's start by looking at this sample problem. So similar to the previous case, which is a charge ring, here we still have a light charge, but it is not a whole circle. It is only an arc. So here, a plastic rod have a uniform distributed charge, negative Q. The rod has been bent in 126 circular arc of radius r. So this is radius r, and we place coordinate axis such that the axis of symmetric rod lies along the x-axis. So it is totally 120 degree, and then we place the x-axis and the rod here so that we have positive 60 degree here and negative 60 degree here. So and the origin is at the center of the curvature P. So this is the center of this arc. So in terms of Q and R, what is the electric field E due to the rod at point P? Okay, so here we still do similar things. Which is like we know that the whole charge negative Q are uniformly distributed on this segment, and we try to separate this whole arc into many infinitesimal small segment, ds. So as much as it is symmetrical to the x-axis, which means that if we pick ds at the quadrant or at the first quadrant, then we can for sure find the symmetric element ds prime at the fourth quadrant here. So as much as it asks you the electric field generated at point P, which means the origin of the coordinate axis. So we would like to find the E field at this point. And as much as the charge is a negative charge over this rod, so ds is also negative, ds prime also negative. So the dE generated at point P by ds should pointing to the upper right, and the E field generated by the ds prime should point to the bottom right. Okay, and as much as this is uniform, so dq here should be equal to the dq prime here, and the distance from ds to point P and also ds prime to point P should be the same. Because it is a part of a circle, so it is the radius. So as much as the charge are the same and also the distance are also the same, then they should generate the E field with the same magnitude. Of course, the direction are not the same, but we can see ds generate dE, should have a magnitude to be the same as dE prime. Okay, so if we try to decompose these two vectors on the project them on the x-axis and y-axis, we know that DEX will add together, and DEY by DE and DEY prime, maybe I can say this is DEY prime. DE right and DEY prime should also be the same, should have the same magnitude, but they point to the opposite direction, so they cancel out. Okay, so we only need to consider the x-axis component of the E field. It will not generate in other E field on other axes. So let's see. So DE will be nothing but K times DQ. We have DQ here, and over the radius is small r. So we use r square here. So this is nothing but the E field generated by a point charge, because we already assume this segment is infinitely short. So so likewise, we can also assume the line charge density, line charge density, which is like Q will be this segment is 120 degree, but actually we need to convert it into the radius. So 120 degree turn to radian. I mean radian. Radian. So we should divide it by 180 degree and multiply by pi. So it will be 2/3 pi. 2/3 pi. So 2/3 pi, which is this angle in radian, and multiply by the radius r. So this is the length. This is the length. The length of this rod is 2/3 pi r, and then multiply by the line charge density. So this is the length. This is the density. Okay, so here we can write it as K times lambda ds over r squared. So which is nothing but the length here multiplied by the density, which is uniform over the whole rod. Okay, so the next step is we try to find the x-axis component, which is dE. Then we know that this is theta. This is theta. So the x-axis component will be dE cosine theta. So which is nothing but K times lambda ds over r squared cosine theta. So we just move this term here. Okay. So the next step, so the next step, as much as we have the variable to be theta, but here we have ds, so that we need to do some variable change, or just a u substitution, so that we make this one to be d theta, so that we can finish off this integration. Otherwise, here we have ds and theta is an other function, then there will be some problem for the integration. So, and you know that, so this is ds, this will be d theta. And if the radius is r, so you know that ds should be r times d theta. Okay. So we will have k times r lambda d theta, and then over r squared cosine theta. So we just substitute ds to be this term, So we have r d theta here. Okay, so next we can actually cancel out r and this square. Okay, so now we can try to do the integration, because we know theta could be from here is negative 60 degree, or in radian, which is minus pi over 6. This is 60 degree, which is pi over 6. So we can try to find the overall E, which is the integration of a dEx. Okay, over this rod L. So put an L here. So DEX is actually this one. So we just plug it here. So we have a integration of a K lambda over R cosine theta. We put it in the front and d theta. So it's just like the normal form of the integration. Okay, so this is constant regarding to the theta. And of course, we know the lower bound should be minus pi over 6 and pi over 6 here. So, okay, you can just put this term out of the integration. So we have a k lambda over r, and then integration of cosine theta d theta minus pi over 6 to pi over 6. Okay, so the antiderivative of the cosine theta should be sine theta. Pi over 3, yeah. Yeah, pi over 3, yeah, you are right. Okay. Yeah, pi over 3. Thank you. Yeah, pi over 3, yeah. So the antiderivative of cosine theta should be sine theta. So we have a k lambda over r, and then times sine of theta, and then evaluate from minus pi over 3 to pi over 3. Okay. So yeah. So sine of pi over 3 is the square root of 3 over 2. Yeah. So this becomes square root of 3 k lambda r. Or you can write one more step, which is sine of pi over 3 minus sine of negative pi over 3, like this. So we will get square root of 3 k lambda over r. Yeah, and actually we should not stop here yet, because lambda is what we assume. So we try to eliminate it. So from this equation, we try to move this term to the left side. So we have a lambda equals 3q over 2 pi r, like this, and then plug it back to here. So in that case, we can eliminate lambda with the original q. So we have square root of 3k over r times 3q over 2 pi r. So it becomes 3 times square root of 3 kq over 2 pi r square. Actually, you can, yeah, you can just make it a number, but it depends. I think this may be good enough. Yeah, this may be good enough. Yeah, so this is the answer to this problem. So any questions? Yeah, if you have question, please leave it on the comments. I'll try to see it. And yeah, so let's move on. Okay. Okay, I still have one more. Yeah, so next we have a checkpoint tool, which is quite simple. So it just let you to familiar with how the EVU can be add and or cancel. So here it shows 3 non-conducting rod. Non-conducting rod means so this keyword is actually means the charge on the rod cannot move, and that's it. If it is conducting rod, then you will try to consider the charge may move to somewhere else. Yeah, and usually for maybe for a sphere, the charge should always distribute on the surface rather than distribute inside. Yeah, but for non-conducting sphere, something like that, then the charge may be non-uniform or even in a non-uniform distribution. Yeah, so yeah, because the charge in the non-conducting object is not movable. It's not movable, so that you can try to have some strange charge distribution rather than something like uniform over the surface, something like that. Yeah, so here, let's move on. So one circular and two straight. So part A is circular and BC are straight. So it has uniform charge of magnitude Q along its top half and another along its bottom half. So for each rod, what is the direction of the net electric field at point P? So the dark part means it has a positive charge, and for the light part, it means that it has a negative charge. So for part A, it will be simple because for this part, it is symmetric, and it is a positive charge. So at point P, the E field should point to this side, 45 degree, pointing to the top right. And for this part, it is negative Q, so it should point to the top left. And the x-axis should cancel each other. So finally, the E field should point to the positive right axis. So for part A, it should be pointing up or positive y-axis. Both are okay. And for part B, question B, for the top part, it should point to somewhere here. Actually, the angle should be calculated to know, but yeah, so for this question, we don't necessarily need to know what is the angle for this one, because yeah, you cannot really tell because you don't really know the length. So yeah, it's hard to tell. You don't actually know the length of this part and the length of this part, so yeah, you cannot know the angle here. But at least we know for the top part, it generates the E field, pointing to the bottom right, and for the bottom part, it generates the E field pointing to the top right. So the y-axis component will cancel each other, and the overall E field should pointing to the right side or positive x-axis. Okay, so for the third part, likewise, for this part, the E field points to the bottom right. And for this part, it is a negative charge, so it should point to this side. So the x-axis component cancel. It should pointing downward, or negative y-axis. So it's a quick checkpoint. Okay. So I think it is easy. So let's move on. Okay, so now we consider another case, which is the E field generated by a charge disk. So rather than a charge ring, we have the whole disk. Okay, so the E field generated by the charge ring. So this is the E field generated by the charge ring. Okay, by the charge ring, not for the charge disk. And yeah, so now we try to see how we can separate this disk into small part we can handle. So probably yeah, maybe you have learned the calculus. You have tried to, you should have tried to calculate. I'm not sure. Yeah. Maybe you should have learned in calculus class that you can try to integrate the area of a circle. So it will be something like integration from negative r to r and then square root of r squared minus x squared dx, something like that. Something like that too. Yeah, and then multiply by 2 because this part only regarding to the top part of the circle. And in that case, we integrate the area of a circle over the x-axis. So it's somehow like we try to cut the circle like this, cut the circle like this. And of course, this is not enough. We still need to cut it like this. Okay, cut the circle like this so that every part is a small area, and then we will try to we can try to assume it to be something like a discrete charge, and then we can apply the dE equals blah blah blah, and then we try to integrate that over the x-axis and y-axis. But this will be difficult, as you know. Integrating this is not easy at all. At least you need to something assume like x equals to r cosine theta, something like that, and then substitute there and then do some change of variable. So it is not easy. So we may try to consider another way to cut the circle, like, okay, we can try to cut the circle like this. Cut the circle like this. So using radial 镜像的 and also something like this. Oh, I cannot draw it very well. But actually, there are some concentric circle, 同心圆. And so every part is also some small area. Actually, they are not perfectly a rectangle, but yeah, as you may have learned, it is something called a polar coordinate. Polar coordinate. So we can integrate over the r-axis and theta axis. And yeah, which is something like this one. Yeah, actually something like this one. But as much as we have already integrated over let's say, because we have already considered the consider the charge ring. Consider the charge ring, which is something like we have already considered the case integrating over this direction. So in this case, we can make sure of this result. So we can regard a whole disk is like we have many different rings with different radius, and then we try to add them together. This is the idea. So so in this case, yeah. So rather than writing it as E and Q, we change it to DQ due to this ring. And the E field generated by this ring is DE not E, and then we try to integrate the E field generated by this kind of ring with a different radius from 0 to capital R. As long as we try to integrate them, then it forms a whole disk. The idea is like that. Okay, so here, yeah. So actually, at that time we use the capital R here, but here still capital R refer to the radius of the whole disk. So when we consider this ring, we should use small r here. So we also change this capital R into small r. This capital R into small r. So this is pretty much like that. Okay, so we have this expression. And yeah, and the point here is that so we have a dq should be something like the density. Now it is not a line charge density anymore. It is surface charge density because it is an area. This is an area. And this area is somehow like this 2 pi r dr. 2 pi r dr. So why it will be like that? Because you can imagine this is a ring. This is a ring. This is not a rectangle, but as much as this ring is very, very thin, because the thickness of this ring is only dr, so it is very, very thin. And we try to cut it from some point, and then we try to expand it. So it will something like a rectangle. And the height is dr, and this width will be 2 pi r. So the area of this ring after expanding it will be something like this. So we can just substitute this part into here. So we get this one. And we can just gather some of the variable. We can simply cancel this 2 and 4. Cancel this pi and pi. So, or maybe we can just keep this 2 and 4. Maybe we can just keep it. So here we have a 4 epsilon naught, sigma here, z here. And then the remaining terms related to dr. So we keep 2r here. Maybe I change another color. So yeah. So you have 2r dr. So you have a 2r dr here. And then this term is here. So we get dE. dE is this expression. Okay, so next we would like to do the integration. This integration is not that difficult because we can simply use the change of variable, just like the reverse case of the chain rule. So 2r dr is nothing but the dr square. So you know dr square dr is something like 2r. So we move this one here. So we have 2r dr equals dr square. Okay. So as much as we add another constant there, then the derivative of a constant will be 0. So this z square is not related to r. So it doesn't really matter. So we can just move this part here. So it's just like the chain rule. We have this one and this one here. So maybe you can just if you don't get comfort enough, you can just write y equals r square plus z square, so that it is actually something like sigma z over 4 epsilon naught, and the integration of y to the minus 3 over 2 power dy, something like this. Okay. So and of course you need to change the upper and lower bound by plugging in 0 here for the r. So here we have z square, and if you plug capital R here, it becomes r square plus z square, something like that. Okay, so this is nothing special. It is something like integrating the polynomial. So we just add 1 to the exponent and then divide this exponent. So this is very easy. And yeah, so we need to evaluate this term from 0 to R. So we plug in R here, plug in R here. So we have R squared plus capital R squared plus R squared, and then take the square root and then 1 over this term. So, and then we have a negative here. So we have this negative term, and then 0 here, plug in here. So we have a C squared, and then take the square root, 1 over this square root of C squared. And then this 2 and this 4 is cancelled. So we turn out having this expression. Still, we only consider the E field over this axis, over this Z axis. This Z axis is perpendicular to the disk and also passing through the center of the disk. And yeah, furthermore, we can still maybe we can also distribute this Z into here and into here. So this Z and square root of Z squared cancel, it becomes 1. And this Z and this one, yeah. So we have this term. Something like this. Okay. So this is the precise expression for the E field generated by the whole disk. And here we also try to apply the far field assumption here. By assuming that R is no, this is not far field, sorry. This is not far field. Here we assume that this is infinitely large. Sorry. Yeah, here we assume that the disk is infinitely large, which means R, capital R, tends to infinity. So we have a really, really, really large disk with many charge. Yeah, actually infinite many charge, because the density is finite. If the area is infinite, then it's somehow like sigma times an infinite area. There will be infinite many charge. But the case here is that if we assume capital R is infinity, which means that this term will be 0. This term will be 0. Yeah, this term will be 0. Why? You can just try to so for this term only, you can just divide out on the top and the bottom. So we have 1 plus Z square over R square, or maybe we can just put it out, something like this. So now if R is much larger than Z, because R is infinite, Z is finite. R is infinite, Z is finite. So this one is 0. This one is also 0. So 1 plus 0 here. So this is 1 for the denominator and 0 for the numerator. So this one tends to 0 as R is much larger than Z. Okay, so this term vanish. If we assume that R is infinitely large. So this is a very elegant expression for the E field, which means that if we have infinitely large charge disk with uniform charge distribution, then it will generate the E field, which is a constant. Epsilon naught is a constant, 8.85 times 10 to minus 12. This is sigma. We assume the charge density is uniform over the whole disk. So this is nothing but a constant. So this is very important. So here we let you know if we have infinitely large charge plate, it generates E field, uniform E field over the whole space. So on the upper part, the E field pointing upward. And then for the bottom part, the E field pointing downward. If this charge is positive, this charge is positive. If the charge is negative, then it will be the other way around. If the charge is negative, then it will be the other way around. The E field will be pointing to the plate. Just follow what I mentioned yesterday, the electric field line. So now you can try to understand why the electric field line is like that. So it generates a uniform E field over the whole space. Okay. So here, it used this result. It tried to explain the mechanism of the inkjet printer. 喷墨打印机 So if a particle with charge Q is placed in an external E field, and electrostatic force F acts on the particle F is F equals QE. So this is the definition of the electric field. So for the definition, it is like E equals F over Q, something like that. So we just put it here, so we get this one. Okay, so for the electrostatic force acting on the charged particle located in an external E field, E blah 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 blah. So if the direction of E, if the charge Q of the particle is positive and has the opposite direction if Q is negative. Okay, so here, let's see this figure. So we have the ink here. So this is green, so it denoted by capital G, or maybe it's just stand for the generator G, but at least it's shown it in green color. Yeah, so if we have some ink pack here, when the printer try to print out some green color, it try to inject an ink to the right side. And actually, here is the control part. It try to add some charge. To the ink. Let's put a green dot here. We add some charge, negative Q, a negative charge. And suppose we have positive charge plate here and negative charge plate here. Even though it is not infinitely large, but at least inside this region, it is close to uniform E field. It is close to uniform E field. So as much as we have positive plate, the E field will pointing downward, regarding to the top plate. And for the bottom plate, it points to the same direction because in the middle region, because the E field should pointing to the negative charge and should be pointing away from the positive charge. So inside this area, it generates the E field pointing downward. So here, this is a negative charge, which means that as long as this ink go to here, inside this E field area, then there will be a force acting upward because it is a negative charge, negative Q. So there will be a force. So it's something like what you have done in high school physics, just like if you have something moving to the right side and you have something like mg, which is a gravitational force, and you have a v, initial velocity, moving to the right side, then due to the force, then it will be something like a parabola locus. So it will be something like this case, but this is not the gravitational force. This is due to the electrostatic force. So inside this region, it is a parabola. So out of this region, there will be, we assume that the electrostatic force is weak enough. So after this region, it is a straight line. This is a straight line. And this is parabola. Okay, something like this. So drops off from the, yeah. So as much as we can try to control the amount of Q so that we can make the ink shoot to different position to print out some text or image that we would like to. So this is the paper. Okay, so this is a simple explanation for the mechanism of the inkjet printer. Okay, so let's see a sample problem. Okay, so the deflecting plate of an inkjet printer with a superimposed coordinate axis. Okay, so the mass is this one, very light, 10 to the minus 10 kilogram, and a negative charge of a Q like this. Okay, so the initial velocity, Vx, is 18 meter per second. And the length of each plate, so this is the length of the plate, is 1.6 centimeter. So the plates are charged and thus produce electric field at all points between them. Assume the field downwards directed, uniform, and has magnitude with this magnitude. So what is the vertical deflection of the drop at the far edge of the plate? The gravitational force on the drop can be neglected. Okay. So so as much as we know, the x-axis velocity is 18 meter per second, and the length is so this one is the Vx, and the length is 1.6 centimeter. 1.6 centimeter. This is Vx. This is 1.6 centimeter. So we will we can calculate the time when the charge goes from here to here. So this is L over dx. And don't forget to convert it back to the SI unit, which is meter, not centimeter. So 1.6 centimeter is a 0.016 meter, and over 18 meter per second. So this is this is 1 over 1125, which is 8.89 times 10 to minus 4 seconds. Okay. So yeah. So next part is F equals QE. So there will be a electrostatic force acting on the ink. So Q is this one. Q is this one. E is this one. So yeah, we can actually use capital Q here because yeah, we provide capital Q. So it is a 1.5 times 10 to minus 13 times 1.4 times 10 to the 6th power, which is 2.1 times 10 to minus 7 Newton. Okay, for high school physics, you know that y should be 1/2 at squared. And according to the Newton's second law of motion, F is ma, which means that A is F over m. So we have F over 2m times t squared. So we have already know that F is 2.1 times 10 to minus 7 over 2 times the mass is The mass is 1.3 times 10 to minus 10. So 1.3 times 10 to minus 10 times this one, 8.89 times 10 to minus 4 square. So this is 6.4 times 10 to minus 4 meter, or you can write it as 0.64 millimeter. Yeah. Yeah. So this is pretty easy, I think. Okay, so next we still need to talk about the dipole in an electric field. Dipole in electric field. So it's just some definition. So as much as you have learned the classical mechanics in physics 1 or high school physics, you know something called the torque. The torque in Chinese it is called 力矩. Okay, and yeah, potential energy 位能或者势能yeah. So so it tells you about the torque for the electric dipole, in the electric field, in the uniform electric field. Okay, so yeah, so it directly tells you that the torque for the dipole will be P cross E. So this is the cross product. We will have learned much more about it in the second half of this semester, which is about the magnetic field. We will frequently use the cross product, that part. But for the electric field, we will seldom face this cross product. We usually use the dot product rather than cross product in the electrostatics. Yeah. And so far you only need to know that if we only need to calculate the magnitude of the cross product, it is somehow like PE times the sine of theta, which is something like P, as much as we have P is a vector, E is another vector. So this is sine theta, which is the angle between these two vectors, and P cross E is somehow like the area. P cross E is somehow like the area of this parallelogram. Okay, why it would look like this? Let's see this figure. Okay, so now we assume that we have a uniform E field pointing to the right side. So how to generate it? Actually, is somehow like we have a positive plate on the left side, and then we have a negative plate on the right side, and you will generate a uniform E field pointing to the right side like this. So we just erase it. Okay, so now we assume that we have an E field here, and then now we have a dipole. Q, we have positive Q and negative Q, because the definition for the dipole is like it has the same amount of charge with different polarity, positive charge and negative charge with the same amount, and then keep in a small distance, d. So we know that the dipole moment P is defined as T equals QD, if you still remember. D is the distance vector from this point to this point. Q is the charge here. So now you can imagine for this positive charge in the uniform E field pointing to the right side, there will be a force acting to the right side, pointing to the right side. And and for this negative charge, suppose the E field pointing to the right side, so the force acting on this negative charge is pointing to the left side. So in this case, you imagine there is some bond to hold these two charges. it cannot really move. It's just like a rod. It's just like a rod. And if you just try to pull this end to the right side and pull this end to the left side, then this thing will try to rotate. This one will try to rotate. Yeah, something like that. Okay, maybe yeah, it's hard to show. Even I open the camera, so you can try to imagine like this. So this one try to push it here to this one try to push it to the left side. So this one will try to rotate. And if you have ever learned the cross product, yeah, you should have learned something like the cross product in high school physics. So you should know the right-hand rule. So for the P, so you use your forefinger pointing to the direction of P, and then you try to cross it to the E field, which is something like this is P, this is E. And then your thumb will pointing into the page. Which means that you use your forefinger pointing to the P direction, and then you try to cross to the E field. This is E, this is P, this is P. And then you try to cross, your thumb should be pointing into the page. The cross means into the page. If it is a dot, it is pointing out of the page. So your thumb pointing into the page, which means that the direction of the top should be pointing into the page. And as much as it is rotating clockwise, 顺时钟转的. So it follows the right-hand rule. So right-hand rule. So your forefinger follow this direction, and then your thumb pointing into the page. So this is pretty much about this torque, the relationship of the torque and this one. And of course, it will store some of the energy. The potential energy stored in this system is like minus P dot E. So which means that if this is the E field, I do not draw too much. And suppose the dipole is something like this, which means the P also pointing to the right side. And in that case, cosine theta is 0. Cosine theta is 0. Cosine theta is 0 in this case. Theta is 0. Cosine theta should be 1. But with this negative sign, which means this is the lowest potential energy. And if it is the other way around, if the dipole is something like a positive on the left side, negative on the right side, in this case, theta is 180 degrees. Cosine theta is negative 1. So with this negative sign, it becomes the maximum U. This is minimum U. So which is something like if you have a curvature like this and you have a ball, if you just ignore the friction force, then this ball will just roll down and then go up. Some of the potential energy will change to kinetic energy. And then after this part, there will be many kinetic energy, and then it goes up and then it becomes lower. And go to this part, all the kinetic energy transfer back to the potential energy, and then it will going back and forth forever if there is no friction force. Yeah. So this is somehow like that case. It is something like if the initial condition is like positive charge and negative charge like this, and then you have a E field pointing to the right side, then it will try to rotate here, and then rotate to here. So as much as it rotate up to here with a symmetric position, it will go back, and then going back and forth. if there are no fractional force. So something like that. So it is something like the potential energy. Okay, it's something abstract, but yeah, just let you know. So here we have a simple sample problem, actually two. So let me finish this off before we have a 10 minutes break. So here, okay, it tells you that we have a clock face has negative point charge, negative Q, negative 2Q, so on and so forth up to negative 12Q, fixed at the position at the corresponding numeral. So the clock hands do not perturb the net field. Doesn't, yeah, just ignore it, and this is good enough. So what time does the hour hand point in the same direction at the electric field vector at the center of the dial? So it tells you that now we have a circle. Sorry. We have a circle. A circle should be something like this. Yeah. So we have a 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, the clock face. I hope you still know what is a clock face. Yeah. So it tells you that for 1, we have negative Q here. We have negative 2Q here. We have negative 3Q here. So on and so forth up to here, negative 12Q. Okay, it asks you what is the direction? What is the direction of the E field? The direction of the E field. And then it asks you just what time it will be. The clock hand, the hour hand point in the same direction as the electric field. So of course you need to know what is the direction of the E field. So we can use the concept of the cancellation. Ouch. Yeah. Okay. So first of all, we have 1 and 7. So we have a negative Q and negative 7Q. So it turns out to be for this negative Q, it generates the E field pointing to this 1. And then for this minus 7Q, is generate the E field pointing this side. And of course, this is 7 times larger. 7 times larger. This is 7 times larger. This E7 is 7 times larger than E1. So part of them will cancel. So it will turns out to be, ouch. It. Okay, so it turns out to be something like this. So it is proportional to 6Q, proportional to 6Q, pointing to this 7. And of course, we can also do the same thing for 2 and 8, which means that for 1 and 7, there will be a E field pointing to the 7, which is proportional to 6Q. And for 8 and 2, it will generate E field pointing to this side with the same amount, because 8 and 2 cancel, there will be 6Q, proportional to 6Q. And 9 and 3, we have something like this, 10 and 4, something like this, 11 and 5, and also 12 and 6. So we will pretty much have a 6 E field vector pointing to different direction, but with the equal magnitude. And also the angle between each of them should be the same. So we can at least know the direction after they are adding up. After they are adding up, they will turn out to be something like 9 o'clock, 10 o'clock, and then it points to right between these two. So the E field, the overall E field should point to this direction. And of course, this should refer to 930. 930. Okay, so this is an easy example, but just to apply the cancellation for the E field. Okay, so the next one. So suppose you design an apparatus, 仪器, in which a uniform charge disk of radius capital R is to produce an electric field. The field magnitude is most important along the central perpendicular axis of the disk at a point P at distance 2R from the disk. So cost analysis suggests that you switch to a ring of the same outer radius R, which means that you just remove this part. You just remove this part, and you still keep the charge density. You still keep the charge density. Yeah. But you only use the material for the outer ring. Yeah, not a thin ring, but yeah, with half of the radius. So assume that ring will have the same surface charge density as the original disk. If you switch to the ring, by what percentage you decrease the electric field magnitude at P? Okay, so assume that this one is A. This one is A. So according to what we have derived earlier, so EA will be something like sigma over 2 epsilon naught 1 minus. At that time we have E equals sigma over 2 epsilon naught 1 minus Z over square root of Z square plus R square, something like this. And now this distance is 2R, so which means Z equals 2R. So we just plug in Z equals 2R here. So here we should have 2R over square root of a 2R quantity square plus R square. Okay, so if we just simply simplify it, we will get sigma over 2 epsilon naught, and then the R and R square will be cancelled. So it turns out to be 1 minus 2 over square root of 5. And then we actually don't have a closed expression for the blue ring, but we can actually calculate the inner part and we can subtract it. So we assume this part is B. So EB will be sigma over 2 epsilon naught 1 minus here is still 2R because this is still 2R. So this is still 2R here, 2R, but the radius now becomes half of R because the hollow part. Okay, so here after some algebraic simplification, we know that this is 1 minus 4 over square root of 7. Okay, so yeah. So we know that EB over EA is something like, yeah, this part and this part will be cancelled. So we have 1 over 4 over square root of 7, 4 over 1 minus 2 over square root of 5, and times 100%. So this is 28.3%. Yeah, so we can assume that this is EA, this is E hollow. So the reduction by 28.3% if we just make this part hollow. Okay. Okay, so now we have finished off this chapter. We have a 10 minutes break and we will continue chapter 23.